Student. Today I am going to discuss Patterson method, heavy atom crystallography, and isomorphous replacement and molecular replacement. So today is the main topic of the 15 mark question in the crystallography. Last class we have to discuss structural factor, scattering factor, atomic form factor in crystallography of the crystal structure. Now we shall move to the Patterson space. First of all, what is phase problem? We can't measure the phases. X-ray detector like film, photomultiplier, tube, CCD, etc. can measure only the intensity of X-ray, which is amplitude squared, but we needed the full wave equation, that is AE I alpha. We have to see in the previous classes for each reflection to do the reverse Fourier transform, and because it is called as phase problem, the process of getting the phases is called solution. That's why we solve the crystal structure instead of measured or determined. So this is a phase is more than amplitude. This is a, we have to see the example, small example, that is A belongs to small duck. This is B belongs to small cat. So in which the Fourier transform should be a scene. This is a color shows the phase angle, the darkness shows the amplitude. So combining the two four diagram, we have to see in the duck intensity and cat phases and alpha and beta and gamma of the different ducks. So combining the amplitude of the ducks with the phases of the cat, the reversing the Fourier transform, we get the cat. So similarly, this is a cat in which the Fourier transform in the phases we have to see. So similarly, the molecular replacement, if the structure of the molecule is known as approximately, then the phase can be calculated. But we need to know the how the molecule is oriented. This is a different oriented in the same symmetry, same molecule, same symmetry, same cell dimension, but these two crystals are isomorphous. These two crystals are isomorphous. This is the changes in the rotation that is called as oriented. Orientation should be a changes in the molecule and symmetry. So similarly, we can use homology to interstructure. If the protein sequence identified is less than 25%, then infer that sequence are homologous protein have similar structure. So if homologous of known structure exists, then it can be used to do molecular replacement. The unknown is the orientation, the space of all possible rigid body transformations of a molecule has 6 dimensions, 3 angle of rotation, and a 3D translation vector. So this is the equation x dash, y dash, and z dash, or x dash equal to cx plus v. Therefore, the position of our molecule in the crystal unit cell must be a 6D transformation. 6D transformation of its current position. Molecular displacement, molecular replacement is a method for finding the angles and a vector that defines the transformation. So this is a, now we shall move to the another topic that is called as a Patterson space. Patterson, by considering the following amplitude for two atom crystal are maximal when the atoms align with the Bragg plane. So this is the plane, two symmetry related to heavy atoms in which the lattice plane, that is f of HKL, should be scattered in the different phases if they have the same phases, any phase, it doesn't matter, then the amplitude is greatest. This is a two heavy atom. Though constructing a Patterson method, if this plane have largest amplitude, the atom must be a the atom must at intersection of this Bragg's plane doesn't require phases. So phase 0 Fourier transform. This is a two atom in the Fourier transform. If we calculate the inverse Fourier transform with all phases set to 0, the wave crest of electron density, although the origin, but the other places where wave crest intersect or the relative position of heavy atom. The phase 0 inverse Fourier transform is called Patterson map. This is the map in which the x-axis and y-axis, this is the similar to Miller indices in which the crystal should be a heavy atom. So similarly, the reverse Fourier transform versus Patterson function. This is a two equation which is called as a reverse Fourier transform and Patterson function. So reverse Fourier transform with phases rho of r equal to summation over h mod of f of h e power I alpha h e power minus 2 pi h into r. This equation shows the amplitude. This equation shows the exponential will shows the phases. So similarly, for reverse Fourier transform without phases. So this is the same equation in which the alpha position should be changes. There is no phase. There is no phase. So this is the Patterson function in which the no phases in the without phases. So similarly, the Patterson map represent all interatomic vector. To generate a center symmetric position in 2D, draw all the interatomic vector, then move the tiles to the origin, the heads are wave. For example, glycine is an example of phi atom in which the vector should be a move in the similar direction. This figure shows the phi atom should be a changes and scattered from the different origin in which the each vector should be a changes. So similarly, the Patterson map for glycine in P1, the unit vector peak should be a changes at the ground state. Similarly, the translational symmetry peak should be a changes reassemble in the Patterson map. So for small molecule, geometry problem can be solved in the stereosymmetry, that is bond angles, bond length of the molecule should be a changes. This is the reverse. So without reverse, the problem can be solved in the geometry. So similarly, the rotational function target molecule should target structure can be refined in the target Patterson. Similar, the search model can be refined the search model Patterson. Rotating search model Patterson should be a matched target pattern. This three A, B, and C should be a rotation function of the different crystal structure of the different value of the different Patterson method. Similarly, the rotating the Patterson, the heavy atom should be a changes in the intermolecular vectors. This diagram shows the intermolecular vector at the translational symmetry. Translational symmetry. Similarly, the intermolecular should be a changes in the intramolecular vectors. The origin should be a dark position. Look at the dark position should be a change from the transform differently. So the correlation function between any two function x and y defined as r equal to summation x minus x bar y minus y bar divided by root of summation over summation x minus x bar whole square summation y minus y bar whole square. X and y are the function with the same range. X bar means the mean value of function x. So similarly, r equal to 0 because r equal to 1 in the correlation and anti-correlation r equal to -1. So similarly, after calculating the correlation function, if there is no correlation, so r is close to 0. So similarly, the Patterson correlation function should be a changes in the Patterson, observed Patterson and rotate model Patterson. So P of mod V minus V mod P bar mod equal to rotate Patterson method at V mean correlated if the spherical cell of the Patterson map that includes a self-peak and very large vectors. So similarly, the rotation function of three-angle alpha, beta, gamma define all possible rigid body rotation. This is a rigid body rotation in which the rotation should be a different angle. The highest Patterson correlation function should be a changes in the alpha, beta, and gamma. So the possible terms in the rotation function should be a changes. So non-crystallographic symmetry can be deducted using the self-rotation function if the native Patterson is rotated against itself and the correlation is calculated. The result will have a non-symmetry related position only if the asymmetry unit has non-crystallographic system. So the non-crystallographic symmetry should be a changes in the P of R. So translation function. Before we have to see in the rotation function. Now we have to see in the translation function. This is the two types of diagram in which the green which shows the translational vector. It should be changes in the cell axis from the different unit cell. So how it should changes from one position to another position. The model is orientated with respect to the cell axis, but still at the origin, we need a translation vector to translate the model to its position in the crystal unit cell relative to the origin. So translation function should be a changes in the different coordinate. A translation of the coordinate is x equal to x plus t. Symmetry position are calculated using m comma v. So x dash equal to mx plus v. M is the matrix and v is the vector. After combining the both equation, x dash equal to mx plus v. So mx m of x plus t plus v. So after calculating the equation m of x plus m of t plus v. So similarly, the translational function can be calculated by f of calculation summation over z summation over g f of g of h e power I 2 power e power I 2 pi h dot is z of r g plus t. So G is known as a all atom, Z is known as all symptoms, and R of G is a fractional coordinate of atom G. T is known as a translation vector. After calculating the translation function, R factor can be calculated by using this equation. So similarly, heavy atom model. The heavy atom method should be in the form of periodic table. So in which the different from 37 to 118, that is called as a heavy atom method. So it should be a dark position. A dark position has shown the heavy atom method. So we can represent a structure factor of known amplitude and unknown phase as a circle in organ space. Radius of the circle is the amplitude. The 2f lies somewhere on the circle. So that is shown as a F. This lies between F and I and R. So similarly, heavy atom isomorph replacement, isomorphous replacement f of p plus f of h equal to f of ph. This is the diagonal shape of the symmetry in which the heavy atom should be lies. So similarly, the heavy atom isomorphous replacement, which is equal to turning proton into a some molecule by soaking into heavy atom. So f of p of h should be a some protein. It will the diffracted from the heavy atom to vector sum. So Fourier transform of a heavy atom derivative is the vector sum of the transform of the protein and a heavy atom. Similarly, the comparing the parent and a heavy atom data set should be a changes. Look at the diagram should be a comparing in the previous section. So similarly, the heavy atom should be changes in the reciprocal space. So upper and lower images are two precision photographs showing the Li equal to 0 level of the reciprocal space. The upper is the original protein crystal. The lower is called a soaking heavy atom solution. So similarly, Harker diagram method for discovering phase from amplitude. IPH plus f of fh equal to f of ph. We know that this equation shows the amplitude, this equation shows the heavy atom, both heavy atom, we know both amplitude and phases. This is known as the amplitude. So this is the single isomer replacement in which the amplitude should be changes in the one heavy atom. There are two ways to make the vector sum of add off. So similarly, the last we have to see single replacement. Now we can move to the two heavy atom derivatives produce unambiguous phases. So this is the equation that is called in the single atom from two heavy atom. This is the diagonal. This is the two circle which shows the one thing heavy atom. Similarly, the two heavy atoms should be a change. So from that, phases are more important than amplitude. We can't measure phases only amplitude. By adding heavy atom, we can change amplitude by a significant amount. This is the two heavy atom in which the single and two heavy atom can be different from the value from the theory of the Patterson map. So if we know that the contribution of the heavy atom, we can solve for the phase of the protein. So single isomorphous replacement gives an unambiguous phases. So multiple you will give the different replacement. So we have to see if we can locate the heavy atom, then we can calculate its contribution. From this we can calculate the f of pH. So similarly, the using a Patterson map to find heavy atom, we can calculate the different isomorphous value from this. So this is the u equal to u zero point 0.5, u equal to 0.46, w equal to 0.24. This is the area should be a changes in the Patterson map to find the heavy atom. Similarly, the Patterson space, having the Patterson space of the Patterson map is the centrosymmetry position, centrosymmetry projection. This is the real space, this is the Patterson space. In real space, phase equal to alpha. In Patterson space, phase is equal to 0. Phase is equal to 0. Using observed amplitude, but the setting all the phases to 0, create a centrosymmetry image of the molecule. So Patterson peak generated by the symmetry operation found around Harker section. So similarly, we have to see in the symmetry oriented is to be a changes from real space to Patterson space, because the Harker section should be a zero point 0.5. This is a Harker section at the heavy atom, so it should be a changes from z is equal to 0 0.5. So this is the area should be a displaced from real space to Patterson space. Similarly, the Harker section tell us the location of the atoms related to the cell axis. Look at that. This is the area we have to see in the previous section. Should be a changes from two-fold divide this vector to the different coordinate. So in which the z position are found in the different intercept. Similarly, non-Harker section tell us interatomic vector or interatomic vector not related by the symmetry. If there is more than one atom, you can get the vector between them by searching for all peaks in non-Harker section of the Patterson. See, we have to see in the previous example like glycine, then combining the knowledge from the Harker section and non-Harker section, we can get the atomic coordinate. So simple case, this is an example of Harker and non-Harker section in which XY position are found in the two-fold axis for each atom. This is a two-fold axis in the Harker section. Similarly, in non-Harker section, one-fold atom, one-fold one atom related to the position. This is the changes. This is the changes from the Harker to non-Harker section. So similarly, the Patterson map can be calculated without needing to know the phases. Patterson map shows the vector between the heavy atom. By considering the symmetry, we can locate the heavy atom sometimes uniquely. If we know where the heavy atoms are, then we can calculate the scattering factor f of h. If we know f of f, then we can calculate the phases. Similarly, after getting calculate the f of h, we can solving the heavy atom Patterson method. So this is the peak of the large circle space group P of 3 1, where the trigonal unit sector unit cell heavy atom are related threefold threefold. This is a threefold in the triangular shape. This would be a screw at the equilateral triangle around the origin such the site or the peaks are known as a Patterson peak. Estimate the coordinates of the triangle vertices. So Hacker peaks are vector between symmetry related heavy atom, that is P equal to V minus M of V. So similarly the finding and using symmetry operators, we can calculate the different space coordinate and crystallography. The two heavy atom derivatives unvicious space we can calculate in the different single from different Patterson map. So similarly, this is the example of phase problem uh, we have to see in. This is a phase problem we have to see in the different circle. This is so from this we can calculate the crystal packing. So another topic that is called as a crystal packing, in which the protein crystal packing intersection or salt bridge and hedge bond mostly. These are much weaker than the hydrophobic interaction that hold proteins together. This means protein crystal are fragile and proteins in crystal are probably not significantly distorted from their native conformation. This is the crystal packing. This should be a bonded from the salt bridge to H bonded mostly. So the hydrophobic interaction should be a reacted from protein crystal to protein probably not distorted. So similarly, this is a useful centric reflection from 0 to 180 degree. So from that we can calculate the uh, centric position of the crystal requiring phase 0 to 180 degree, 0 degree or 180 degree. If non-centric space group has two-fold, four-fold, and six-fold rotational symmetry, then the reflection in the zero plane or centric. So similarly, for centric reflection, this is the equation have shown in the 0 to 180 degree. So similarly, the initial phases are not measured exactly because amplitude are not measured exactly. Error bar on FP and FPH create a distribution of possible phase value. This is the changes in the crystal packing factor from the Patterson method, in which we can't calculate the initial phases. So similarly, from this I have to stop the topic from Patterson method, phase problem, and heavy atom method from the crystal structure in the crystallography. Hope you have to understood the crystallography from the different structure. Thank you.